Now, part C. Let me just check to see if anybody emailed, text. Nope. Okay. Um, part C, right? So now we're doing an adiabatic reversible expansion. So that right there is going to add in a few different factors, right? We're going to be using a lot of different equations in this case. The scenario is a bit different. The, V final that we had previously calculated is going to be different. We're going to have to calculate a new, a final temperature, right? Because the temperature is going to change as well because it's an adiabatic expansion, and stuff like that. However, right, one thing that we can quickly do, right, is we can actually cancel out a whole bunch of values because we already know some things are going to be equal to other things, and we already know some things are going to be equal to 0 as well. So to do that, right, so if we're looking at it, right, we know it's an adiabatic expansion right off the bat. We know that Q is equal to 0, right? That's what happens in adiabatic, right? It's thermally insulated, so there's no heat flow in, there's no heat flow out. Q stays completely 0. The only thing that happens is work. And so that tells us then, right, that delta E is going to be equal to W in this case right here. So all we have to do to calculate delta E is we just have to calculate the work, right? Straightforward, pretty easy peasy in this case. Or, right, like alternatively, right, we can just simply use the definition, right, where to calculate work, all we have to do is calculate delta E, right? So it's going to be a pretty similar process in those cases. The other thing is, right, that we know is that we know this is a reversible process. So if it's a reversible process, we know then that delta S of the universe is equal to 0 in this case. The next thing that we know, right, is that delta S of the system is going to be equal to negative delta S of the surroundings. But another thing that we know, right, because there's no exchange of heat, right, there's no heat flow in or out of the system, right, delta S of the system in this specific case right here, right, is going to be equal to 0, right? Because if we use the equation where delta S of the surroundings is equal to negative Q over T, right, that's going to be equal to 0 in those cases. And so, right, because there's no change in temperature, or so there is a change in temperature, right, but the system, right, the heat flow, there's nothing that's happening going in or out in those cases. And so both of those are going to be equal to 0. So we're already done with delta S of the universe. We're already done with delta S of the system. We're already done with delta S of the surroundings. We're already done with the Q. All we have to do is calculate delta E and the work, right? And we only have to use one equation to calculate what those are, right? Because they're going to be equal to each other. So now going back, right, and thinking about the conditions that we have, right, what we have is that, right, we know that the number of moles is equal to 2.5 moles, right? We know that our initial temperature in this case, right, is going to be equal to 293 Kelvin. We know that the temperature final, we don't know what it is, right? It's an adiabatic expansion, so the temperature is going to change as well. So that's unknown. We know our pressure initial, right? And so that's going to be 2.5 atmospheres. We know our pressure final is equal to 1.00 atmospheres. We know our initial volume, right, from the previous equations, and so that is 24.04 liters. The V final, we don't know, right? Because again, it's an adiabatic expansion and the temperature is also changing. And so the correlation isn't directly the same between the two of them, right? Because the relationship that we're going to have to now use to calculate what the, the final volume is and also the final temperatures is that, we're going to be using the equation, P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma, right? And what gamma is just simply the ratio of the heat capacity at constant pressure over the heat capacity at constant volume in these scenarios, right? And so what we know is that the heat capacity at constant pressure for CO2 is 37.1 joules per Kelvin mole right here. And because it's acting ideally, right, that's what we're saying in this problem, we know then that the relationship between CP and CV is CP is equal to CV plus R in this scenario, right? And we know what R is, right? That's the ideal gas constant, right? 8.314 joules per Kelvin mole. And so to figure out, what CV is in this case, all we have to do is just rearrange this equation. So we get CV is equal to CP minus R. So we can just plug in those values, right? So we have 37.1 joules per Kelvin mole minus 8.314 joules per Kelvin mole. What we get is CV is equal to 37.1 minus 8.314, 28.786 joules per Kelvin mole. So now we can figure out what gamma is using that information, right? So we know what CP is, so that's 37.1 joules per Kelvin mole divided by CV, which we just calculated, which is 28.786 joules per Kelvin mole, right? All of the units cancel each other out because they're exactly the same. So what we get is that gamma is equal to 37.1 divided by 28.786 comes out to being 1.289, right? So that's what our gamma value is. So now that we know what the gamma value is, we can calculate what our final volume is, right? Because we know what P1 is, right? That's the initial pressure. We know what P2 is, right? That's our initial, our final pressure. We know what V1 is, right? Because we've already calculated that previously. So that's going to be the 24.04 liters. So we're trying to figure out what V2 is. So if we take that, all of this info right here, and we rearrange this equation, right? What we get then is that V2 gamma to the power of gamma is equal to P1 times V1 over gamma divided by P2. And then all we have to do, right, is get rid of that gamma. So if we just simply, take everything to the power of 1 over gamma, that gets rid of the gamma for us. And so what we get then is that V2 is equal to P1 V1 to the power of gamma over P2, and all of that over the power of 1 over gamma in this scenario. And I realize that my head's in the way. Right, but I'll just rewrite that over here because it's going to be just as important. And there's really only one equation, right, that we have to pay attention to. And so, and before I jump ahead, right, so in terms of then, in terms of the work, right, all we have to use in this case right here for the adiabatic reversible case, right, is that we know what delta E is equal to, which is going to be equal to NCV delta T. Right, we can figure out what those values are, but we can only figure out what delta T is once we figure out, what the new volume is, and then we can use, PV equals nRT to figure out what the final volume is. Sorry, I realize I'm jumping ahead a little bit, right? But let me go back here, right? So we have V2 is equal to P1 V1 to the power of gamma over P2 to the power of 1 over gamma. And so we take that, now we plug in our values. So we have 2.50 atmospheres times 24.04 liters to the power of 1.289 divided by P2, which is 1.00 atmospheres. And all of that will then be to the power of 1 over 1.289. So if we take everything and we plug all of that in, I'm just going to make it a little bit easier on myself. So 2.5 times 24.04 to the power of 04 to the power of 1.289 divided by 1 comes out to being equal to 150.65 to the power now of over 1.289. And so then V2 now is going to be equal to that value to the power of 1 over 1.289. 1.289, not 12.89. Right, so we get that. And so now V2 is equal to 48.94 liters, right? So very different value from what we had gotten in the previous two, right? So the volume change is, smaller, but that's also because, right, there's a temperature change involved. So now we have V2. And so using that information, right, we can easily figure out then what the final temperature is, right? So we know now what the number of moles are in that case. We know that, what the final pressure is. We know what the final volume is. We know what R is, right? That's the ideal gas constant that we can use. And so now to get, T final in this case, right, this is simply going to be equal to, P final times V final over NR. And so if we plug in our value, so P final is equal to 1.00 atmospheres times V final, which is 48.94 liters, divided by the number of moles, which is 2.5 moles times the gas constant, right? And because now, right, we're trying to cancel out liters and atmospheres, the gas constant that we should be using now is 0.08206 liters atmospheres over mole Kelvin, right? So atmospheres cancels, liters cancels, moles cancels, and then the Kelvin, right? The temperature value jumps up. So we take all of that and we plug all of that in. So we have 1 times 48.94 divided by 2.5 times 0.08206. So what we get is a final temperature of 238.6 Kelvin, right? So we have that value now. So now we can just simply calculate, right? Delta E is equal to NCV delta T. And so the number of moles is 2.5 moles times CV, right, which we calculated up here, which is 28.786 joules per Kelvin, moles times change in temperature, which is 238.6 Kelvin minus 293 Kelvin. And so delta E is equal to 2.5 times 28.786 times 238.6 minus 293 comes out to negative 3,915 joules, right? Because moles cancel and all the kelvins cancel, and you only end up with joules. And that matches what I have here, right? So negative 3,000. Well, I have 3,915 right there. I have on my key like negative 3.89 kilojoules. Again, pretty close, right? It's only a difference of like 0.02. No big deal, right? And so that's also going to be equal to the work, right? And so that is how you get the value of delta E in work for an adiabatic reversible expansion in these cases. So, right. And so those are the things I think, always to kind of pay attention to is how all of that, relates in those cases. So again, right, on your own personal equation sheet, going through, what the conditions are, right? What keywords are telling you what's going on, and then, putting down what's automatically going to be equal to 0, what's automatically going to be equal to each other. And then for everything that you actually have to calculate out, right, putting down what the equations are in those cases to calculate those different conditions. So, but that's how you do B8c, right? So that's how you go through that whole problem. So